for the invitation. Oh, I don't know what happened. All right. So I'm happy to present you today, and the goal, yeah, it's a bit spicy, I should say. Yes, you should use AI for drug design. At Ectos, we are a company specialized in application of artificial intelligence for drug design, organic chemistry. So we have developed two different types of technology: deep generative models to generate compounds, and data-driven retrosynthesis. We have applied this technology in plenty of different projects. So we have tried to make this technology available to any type of use cases and to help researchers on the field to use AI and to accelerate the drug discovery project. So what is artificial intelligence? For me, artificial intelligence is the prediction of complex tasks. As we can see for large language model, do you know Ectos? And I have quite an interesting answer. So you can say, okay, that's quite powerful, quite impressive. And we see recently the power of ChatGPT or other solution. These technologies are quite new, I would say, for people. I would say we are not very experts in the field of AI. But actually, in the field of drug design, drug discovery, those technologies are quite old. I mean, since 2000, since I would say 5-6 years, those technologies are already used. You know, at Iktos, we are doing ChatGPT since 5 years, LSTM, transformers, this type of technology which work on the sequence of characters. In the field of protein structure prediction, you have, you know, graph neural network, transformer. In the field of affinity prediction, the same, retrosynthesis, molecular generation. I mean, there are plenty of fields, and there is an interesting recent review which covers those aspects published in Nature, where they explain how those type of technology can help to accelerate just drug discovery. But, you know, if I want to be a bit provocative, what we heard from the community, from the chemists, from the ComChem, is either I don't believe in AI, or AI for drug discovery is you know, I would say bullshit or something like that. Or, you know, concretely, how does AI can help me in my everyday life? Or maybe you have some people who maybe expect too much from AI and say, okay, it didn't find my preclinical candidates after the first try, so I don't believe in AI. So I will show you just a small video, which has been published recently from Adobe, where you can see live the power of AI, how you can work on a pictures just to add a yellow road lines, or maybe to fill some missing space in the picture. You can also automatic crop selection and add a new background. On this background, you can also add, as I said, red arrow sign. And you can see this look quite impressive. And this is clearly thanks to AI that you can do that. As a final user, you don't care if it's AI or not. What you can see is that it accelerates drastically your job. If you want to do that without AI, maybe you will spend hours to use Photoshop to do that. So it's not a matter of belief or not in AI. Clearly here you can see that AI offers tangible benefits in your job. And what I want to show you today, that it is the case also in drug discovery, because, and we truly believe at Ectos that AI, it's a new tool, but it's still operated by human. It fosters creativity, and people should not be afraid of this type of new technology. So we have worked on two main fields, on three main solutions, sorry. We have developed softwares and services to answer to concrete task and expectation from the chemist. The first one is how to screen massive virtual screening, and we have developed Doc AI. Second one is generative AI against QSAR models or docking and any type of reward function. And the third one is AI-driven retrosynthesis. So first, hit discovery. The challenge of hit discovery is to find rapidly at low cost new active molecules. You know, you are looking for easy chemistry, cheap molecules, fast delivery. So if you consider doing that, usually you will go for docking. But docking cost is 2 cents of euros, 3 minutes per molecules. Of course, you have plenty of way to perform docking, but this is the average price. This type of models can be developed, and again, different use case, you have different scenarios, very nice X-ray information, intermediate case, you can have AlphaFold homology models, and you have favorable case where you have only active ligands, the target is unknown, but still you have different use case, and starting from here, you can design a 3D models. Then once you have a reasonable 3D models, the goal is to be able to find the key which is going to match that lock. And recently, I mean, not really recently, but since some years, I would say, some very famous providers make available huge libraries to 10 to the power of 10, even bigger, of easy to make compounds, and which is most important, very cheap and fast delivery. The problem is that if you want to dock billions of compounds, it will cost you millions of euros, and maybe it takes weeks and years, depends, you know. So this is simply not tractable. So what we have developed at Ectos, it's the Doc AI solution, which combine active learning and docking to find rapidly the most promising hits from those ultra large libraries. The concept is simple. At the beginning of the Doc AI process, we at the first iteration from this billions molecules database, we sample a small set. Then we dock this small set, and we build a machine learning to predict the docking score. Then, thanks to these machine learning models, we can predict the full database because it takes milliseconds, microseconds per molecules. So in a reasonable time frame, you're able to predict the 1 billion compounds. Then you take the best predicted compounds, you dock them to verify if your model is good or not, and you iterate like this among several iterations. At the end, by docking less than 1% of the molecules in one day, you have found all you had to find in this database based on your structure-based model. And you can visually see that after a few iterations, you have converged toward a minima where in your batch of docked molecules, you have low score, which is good for our docking solution. And along the iteration, what you are looking for is the outliers here. Molecules with a very low docking score, meaning a very good docking. And this is what we are looking for along those iterations. We have compared and benchmark our active learning approach compared to the Schrödinger one in the D4 dataset, which is a published benchmark. You have 150 million compounds in this database. You have 10,000 compounds with a top predicted top docked value. Here we are not docking anything, we are just taking this database, and the goal of the exercise here is to see if our active learning approach is able to retrieve rapidly the best score, the best docking score, using the docking score provided by Schrödinger and our machine learning solution. So we have been able to show that by only predicting by only taking 1% of this full database, we are able to cover 75% of the top docked molecules. So it's very interesting to see how fast we converge towards the best candidates. Also, in terms of diversity, maybe not easy to see that on the slide, but you have green, you have blue dots, which describe the molecules as we predicted good, which were good, and in red, the one we missed because we docked only 1%. So maybe we can retrieve the one we missed if we dock more, but the goal is to dock less to get as much as possible. So here, as we said, we covered 75%. But what is interesting here that we cover very well the chemical space. So this approach does not fall into a potential well where you retrieve some active compounds, but only coming from a very special chemical space, and then you are missing all the other diversity. And this is very nice to observe that. We have applied this DocAI approach with the South Korean biotech, and they didn't want to invest too much in terms of chemistry. They synthesize only 30, with the boats, only 30 compounds from MQ and Wuxi at that time. We are working with those two companies, 300 million molecules. Through the DocAI, we have been able to end up to millions molecules. Then we use grid score, clustering, MMGB-assay, manual filtration. We end up to 30 molecules, and from those 30 molecules, we obtain 9 molecules below 1 macromolar, and some up to 20 nanomolar. So we had a very high hit rate, and it was very interesting to observe this level of activity. Another use cases from in collaboration with Medicine for Malaria Venture, where we have applied this DocAI using the enamel reel of several billions of molecules. We have order to enamine 200 molecules. We have received 176 molecules. So in a very short period of time, we obtained almost every molecules we order. So it's quite impressive. And we are waiting for the results. So we had preliminary results recently. We have a lot of active hits. We are still analyzing the results, but the output of this approach seems to be quite interesting. We will see soon. You will be able soon to see the publication of those results. Then once you have a hit, it's good, but now you need to explore around that hit, and this is where maybe those massive virtual space has some limitation, because once you have discovered one scaffold, most of the time around that scaffold you are a bit limited, and then you enter to generative AI. So for that, we have developed Machia, where once you have a hit, you can deconvolute this hit, retrieve the exit vector, and from this exit vector, you will ask Machia basically to find building blocks which can react in the expected position to generate a new molecules. And thanks to that, you can branch this generative AI again to the docking, to QSAR models, to explore rapidly around your hit. And of course, at low cost, because here, what you want to do is to master the chemistry, master also the price of the building block. And in that case, you can reach bigger chemical space, depending on the number of starting material available, the chemistry, the number of reaction you want to apply to the system. You can reach to 10 to the power of 20 of easy to make, cheap molecules. Then by branching the generative AI to DocAI, so again, DocAI is active learning and docking, we have been able to observe that with the same number of docked smiles, docked molecules, we converge much faster with DocAI compared to branch directly the generative AI behind the docking software. So it was quite counterintuitive, but this is the same concept. I generate some molecules. I do not screen. I generate molecules. I dock those molecules. I build a machine learning on the docking score. I generate under the machine learning algorithm. and then again, I take the best one, dock them, update the model, etc. And in that case, with the same number of docked smile, you converge much faster using the dock AI approach. We have applied this technology on an in-house project. So we took a PIM1 kinase as an internal project. We have used the generative AI directly branched to the dock AI technology. We have generated thousands of promising docked molecules. We picked 12 out of it, synthesize it. We obtained 4 molecules with an activity below 5 macromolar, 2 molecules with an activity below 1 macromolar. So it was the first DMT cycle. And then from here, we iterate 2 times with 2 more DMT cycles. So in the total, 3 DMT cycles. And we end up to quite potent compounds with very interesting preliminary ADME data in only 3 DMT cycles and less than 30 compounds. So it's very interesting to see how by generating molecules, exploring the chemical space using AI plus docking plus QSAR models, you can converge so fast toward very active compounds with promising properties. Once you have those compounds, now you want to plug more objectives on it and to perform lead optimization to converge rapidly towards a dozen, even more objectives. In that case, you have different type of generative AI. Here, this is LSTM, but depending again what you're looking for, the constraints, we have plenty of different type of generative AI. And the concept is now quite widely understood by the community, but you have generative models, you have fitness function with different type of predictors, QSAR, docking, dock AI, retrosynthesis, metrics, descriptors, presence, absence of substructures. And then thanks to that, you guide your generative AI toward this ideal chemical space. So in Machia, basically, it's very simple interface where the chemist can upload data, build QSAR models in few clicks, and depending on the use case, we'll use different type of generative AI. Actually, the chemist doesn't care about which type of technology you're using. What they care is they have use cases. Sometimes they want to change the center of the molecules with something quite novel, with something quite similar. Sometimes they want to do fragment growing, fragment linking, following a certain type of chemistry. Sometimes they want to perform small modifications. So you have plenty of cases and you need to cover those cases. And this is what we have been able to do along all those years with all our clients and customers is what do you need according to your stage in your project, and we will make it happen. Don't, whatever the underlying algorithm, we want to produce the results like we saw for Adobe. We don't care about the technology. I want to do that, and how can I do it in a very simple way? Of course, behind Machia, you can plug API, so for application programming interface, where you can directly branch your in-house models, docking score. If you have access to SpaceMax, for instance, provided by Biosolvity, you can also branch those technology during the generative AI process. And finally, in Machia, you have the retrosynthesis, because generating ideal molecules, which is unfeasible, has nonsense. So just a quick video on Machia where I can show you that you can generate basically quite interesting molecules in few clicks. Here it's lead optimization. This is the generated compounds. Here you have the most similar compounds in the chemical space. I can see all the prediction. I can play with the parallel coordinates. I want to see molecules with higher probability on these objectives, higher similarity, better synthetic feasibility. So you can really play with this parallel coordinates to see the generation. Here it's a growing optimization where you define your exit vector, and then Machia will look for a commercial building block which can react in this position to generate the expected compounds. So again, cheap chemistry, fast to maximize certain endpoints. Here it's a novelty generator where you want to do patent busting. So you have your reference molecules and you have proposition made by Machia based on patent literatures to perform patent busting. Again, different use cases, different algorithm. We have a YouTube channel where we present all the use cases which can be tackled by Makia. So have a look. You will, I'm sure, learn a lot of things about our very nice technology. This has been applied in different type of projects. This type of plots are provided by our customers, and they show how, because they want to monitor if the solution is helping them to converge faster. And here you have the number of objectives as the x-axis of the project. Here it's the percentage of molecules which match those number of objectives. Here in this plot, it's quite clear that the initial data set, the top molecules, were maximizing 4 objectives out of 7. And using Makia in the frame of our collaboration, in a few months, we have been able to shift the distribution toward a maximum number of molecules which fix all the objectives simultaneously. With this customer, we have a preclinical candidate right now selected. And it's the same with a lot of other customers where we are, in most of the case, able to showcase the shift of this distribution in a very short time frame. Every year, we have almost one compound which is close to preclinical candidate selection.
Quentin,
And it's
yeah, 2 minutes left.
Oh, I think I had until 15. Okay. Yeah, 5 minutes for the question. Okay. And then Spire, I think we have developed this technology to allow users to find roots. I think you are quite familiar with the retrosynthesis. It's a very complex task. You have plenty of way to break a molecule into pieces. You need to search in this enormous chemical space at a reasonable, as fast as possible at a low computational cost. This type of technology has been used to tackle very complex tasks like chess, Go game. Retrosynthesis is quite similar. We have developed our own data-driven approach to take reaction database, starting material, automatically we build the algorithm to train the retrosynthesis, and it can be customizable on your dataset. I will maybe skip those slides and maybe focus only on what makes Spire unique and how it helps really medicinal chemists. In Spire, you have a lot of advanced search options where you can play with the providers. You can select some providers, avoid others. You can play with the price of the starting materials, delivery times, the number of steps. You can also force the system to pass by name reaction, avoid name reaction, pass by intermediate presence, absence of substructures, but also pass by a given bond you can define. So it's a very versatile tool, and you can have a look to Spire.ai. It's freely available on the web. So to conclude, I would say that AI, it's a new tool. It's nothing more. Without the power of AI, generative AI, retrosynthesis will not be such powerful. Active learning, QSAR model is the same. It's very impressive how it helps to converge faster. And what we wanted to do at Ectos, it's really to put those tools into the hand of the final user, computational chemist, and we believe it's really key for success. Of course, AI is not the guarantee to find your new preclinical candidates, but what we have been able to observe is that ultimately, if you find it faster using AI. And to find a preclinical candidate, it's not only related to AI, but also to the targets, to the biology, to the feasibility actually of the project. So thank you very much for your attention, and I want to thank also the whole team at Iktos who are working hard to implement AI in our technologies.